All right, today we're going to tackle a really core concept in electronics, resistors in parallel. So if you've ever found yourself wondering why adding more paths to a circuit can actually make the total resistance go down, well, you are in exactly the right place. By the end of this, that whole idea is going to make perfect sense, I promise. So here's what we're going to cover. First, we'll do a quick compare and contrast with series circuits, just to set the stage. Then we'll nail down what really makes a circuit parallel. After that, we'll get into the math, but I'll show you some handy shortcuts. Then we'll look at how current behaves, which is super interesting, and we'll wrap it all up with the key takeaways.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, first up, series versus parallel. To really get a handle on what makes parallel circuits tick, it helps a ton to see them right next to what you might already be familiar with, series circuits. And honestly, the main difference is beautifully simple. A series circuit, it's like a single-lane road. All the traffic, or in our case, the current, has to follow that one single path. But a parallel circuit, that's a multi-lane highway. It gives the current a bunch of different paths it can take, all at the same time. And that one idea, it's the key to, well, everything else we're going to talk about. So multiple paths is the big idea for sure. But, electronically speaking, there are a couple of simple rules that officially define what a parallel circuit is. Let's break those down. So here's the deal. Components are considered in parallel when they are connected across the exact same 2 points. We call these points nodes. A really good way to picture this is to imagine you've got 2 main power rails, like a positive and a negative, and all your resistors are just connected between them. And that simple fact leads us straight to the golden rule of parallel circuits. Because every single component is hooked up between those same 2 nodes, the voltage drop across every single one of them is exactly the same. So if you've got a 12-volt battery, every resistor in parallel with it is going to see the full 12 volts. This is so important to remember. Okay, so keeping that rule in mind, take a look at these diagrams. Now, do they all look like the same circuit to you? I mean, they're drawn in all sorts of different shapes and configurations. Surprise! Electrically, they are all exactly the same. And this is such a great way to show that it really doesn't matter how you draw the circuit on paper. As long as those resistors are connected across the same 2 nodes, they are in parallel. It's all about the connections, not the visual layout. All right, let's dive into the math. Now, I'll be honest, the formula for calculating total resistance in parallel can look a little weird at first, especially if you're used to just adding resistors up like you do in series. But don't worry, there's a really solid logic behind it. So here it is. The inverse, or 1 over, the total resistance is equal to the sum of all the inverses of the individual resistors. Now that term, 1 over R, it actually has a special name, conductance. It's literally the opposite of resistance. It's a measure of how easy it is for current to flow. So while the formula might look strange, the idea is simple. In a parallel circuit, you're just adding up the easiness of each path to find the total easiness of the whole circuit. It really just boils down to 3 easy steps. First, you find the reciprocal of each resistor's value. Second, you add all those numbers together. That gives you the total conductance. And then finally, to get your answer back into ohms, back into resistance, you just take the reciprocal of that final sum. You just flip it one last time. Okay, now this is huge, and it's a fantastic sanity check for your math. The total resistance of a parallel circuit will always be less than the value of your smallest single resistor. And why is that? Well, think about it. Every time you add another resistor in parallel, you're adding another path for the current to take. You're literally making it easier for the current to flow, which means the total opposition, the total resistance, has to go down. Now, that reciprocal formula, it works every single time, no matter how many resistors you have. But let's be real, it can be a little slow. Thankfully, there are a couple of awesome shortcuts for really common situations that are going to save you a ton of time. When you've only got 2 resistors in parallel, you can use this super slick formula called product over sum. It's exactly what it sounds like. You multiply their values together on top, that's the product, and then you divide that by the sum of their values on the bottom. No reciprocals needed, and it's way faster on a calculator. So, for example, if you pop a 22K and a 47K resistor in parallel, you run the numbers, and you get a total of 15 kiloohms. And hey, notice something? 15K is less than our smallest resistor, which was 22K. See? The rule holds. Now for the easiest shortcut of them all, If all of your resistors in parallel are the exact same value, all you have to do is take that resistance value and divide it by how many resistors you have. So say you've got three 30-ohm resistors, that's just 30 divided by 3, 10 ohms. It is literally that simple.
Okay, so we've spent a lot of time on resistance. Now let's connect that back to what the current is actually doing. This is where we really see why parallel circuits are so different from series circuits.
Everything that's about to happen here is governed by this fundamental rule called Kirchhoff's current law. And it's actually really intuitive. It just says that all the current that flows into a junction has to flow back out. Current doesn't just disappear into thin air. It's got to go somewhere. And in a parallel circuit, that somewhere means it splits up. The total current leaves the power supply, it hits that first node, and then it divides itself among all the available paths. The cool part is, if you were to measure the current in each of those individual branches and add them all up, they would equal the total current you started with. This table shows it perfectly. Look, the voltage across every single branch is the same, 24 volts. But the current, it's totally different in each branch. The path of least resistance, that 10-ohm resistor, gets the most current, 2.4 amps. Makes sense, right? And the path with the most resistance, the 40-ohm branch, gets the least current, only 0.6 amps. But look what happens when you add them up. 2.4 plus 1.2 plus 0.6, you get 4.2 amps, exactly the total. That's a current divider. Okay, that was a fair bit of info, so let's just boil it all down and wrap up with the absolute must-know points about resistors in parallel. So here it is in a nutshell. Parallel means you've got multiple paths for the current, the voltage is the same across everything, the total resistance is always less than your smallest resistor because adding more lanes to the highway just makes it easier for traffic to flow. And finally, the total current from the source splits up and it's equal to the sum of all the individual branch currents. That's why we call it a current divider. So now you've got a really solid handle on series circuits, and after today, on parallel circuits. But that brings up a really interesting question, doesn't it? What happens when a circuit isn't just one or the other? What happens when you start mixing them together? Well, that's a whole other story.
Thanks for watching.